Hello, today we are going to see an algorithm for sorting elements in an array. This one is called insertion sort. Insertion sort takes an unordered array like 3, 2, 1, 7 and outputs an ordered array like 1, 3, 1, 2, 3, 7. So, like most algorithms in computer science, we are gonna apply divide and conquer. This approach means that we are going to separate the problem in bits and solve each different bit. We do consider the first part of the array already ordered, and we are on the if element of the array. Okay, and we want to go to the next step in which the array will be ordered up to the e+1 element. So the next step will be this. Okay, and this is the e+1 and the if element. Okay, so how do we proceed from this to this? So first we are gonna see the general method that insertion sort uses, starting from the previous array. What we are doing is going from left to right, and for each if element we are gonna go from that if point, back as much as we can with the red arrow until we hit a wall. The wall can be a number that is less than the current number we are taking left, or if we hit the first element. So, for example, here we have 2. In this moment, the array is ordered up to the first element. So the first thing we are doing here is the red arrow. So is 2 less than 3? Yes, it is. So we swap them, 2 and 3. And then we see that 2 is the first element, so we don't keep going left. We stop keep going left. Okay, then we go right with the orange arrow, and from the orange arrow we start confronting 1 and 3. Is 1 less than 3? Yes, it is. So we swap them. Then we go left. Is 1 less than 2? It is. So we swap them. And here we reached the first element. And then last element of the array, is 7 less than 3? No, it is not. So we stop here. And now the array, if we rewrite it, 1, 2, 3, 7, it's ordered. Okay, now let's go to the code. Here I prepared a test class. The only thing important here is the test function, and also a function that I use to check whether two arrays are equal. The base case for a sorting algorithm is sorting an array with one element, in this case an array with the element 1. I'm using the algorithm, the insertion sort algorithm. What is the insertion sort implementation here? I'm just returning the array. My objective here is to pass tests. The first test will be easier to pass. So one element array, I will pass it simply returning array. And then we will be adding complexity to the tests, add more complex tests, and then modify the sort algorithm. So let's see if it passes. Yeah, it does, but let's see it. Okay, it's green. Good. Now we are gonna create a test with 3 elements, and it will have an array with 2, 1, 7. We expect as a result 1, 2, 7. Okay, so on the right, 2, 1, 7. Well, the first thing is to iterate through every element, and this will be the outer loop of the algorithm. Okay, so let's jump to the insertion sort. So we are gonna loop over all the array. Okay, and this is the green arrows, and every time we want to get back as far as we can, as far as we don't hit a wall, and swap while going back. For example, for the first the element of index 1, this element 0, 1, 2. After we used the green arrow, we want to go back. So here we are checking whether 1 is less than 2. Okay, if 1 is less than 2, then we should swap them. 1, 2. How do we translate the orange arrow in code? So first thing, we see that green and orange arrows are separate. So we will create another index called j that starts from the if index and goes back. So this is j represents the orange. Okay, now we want to go back. The first kind of wall we could hit is when we are confronting the first element with the previous element, and there isn't a previous element. Okay, if we are confronting 1 with what? With nothing. If the orange arrow reached the first element, we just exit from the while loop. That means we don't go left, more left than the first element. So we keep going left with the orange arrow while the orange arrow is greater than the first element. Other than that, the second type of wall we can hit, we do see it now. So let's rewrite this array that is now ordered up to the second element. Okay, now we are at this point and we want to go back. Here we won't go back as far to the first element, but we will hit a wall earlier. We are gonna check whether 7 is less than 2. If this element is less than this element, if jth element is less than the j plus 1th element, then we swap. In this case, 7 it is not. This is not true. It is not less than 2. So this is the second type of wall. And how do we code this? So here we don't swap anything at the next pass. All the arrays ordered. Okay. So how do we translate this? We want to continue to move the jth element while the jth element is greater than while it is left than the j minus 1th element. Okay. Oh, oops. Okay. So while I don't hit a wall, what do? I swap. I swap the jth with the jth minus 1 element. Okay, and then I move left with the orange arrow. That means in code j minus minus. And then at the end, after the while and the for loop, the green and the orange arrow, I return the array after I iterated through all the elements of the array. Okay, this sounds good. Let's compile it and then run all the tests. Okay, they do pass. Now, just to be sure, let's see a third test. So in this case, let's make a 5-element test, and let's take the worst case scenario for the insertion sort algorithm. I'll show you on the right. The worst case scenario is the scenario in which an algorithm must do the most of the work. So for insertion sort, it is when you have a array, a decrescent array in this case. So the work here involves doing a lot of swaps. In the first orange arrow does 0 swaps. Then the second green arrow does 1 swap, then 2, the third. Okay, and it goes on 3, 4, 5, n. Okay, so an array with n element, n element does a lot of swaps if it is the worst case scenario. We will see later the complexity of this algorithm in the worst case. But let's check for now if it works for the worst case. So we have, oh yeah, this is 6, not 5. Well, let's make it 5, same thing. Okay, so this has 5 elements and 5 elements. Okay, let's see if it passes. It does not. Okay. Yeah, because this is the expected array. So it's 7, 8, 9, 10. Okay, now we can do it. Okay, all test passes, so the algorithm works. So, as I was saying earlier, let's talk about the complexity of insertion sort. And let's see the worst case scenario that express very good this complexity. Yeah, let's see the worst case complexity actually. So how many swaps do we have to do in an A elements array? This array has 5 elements. So how many swaps should we expect? Green arrow, we are going right, and the first time we do not swap anything, so we do 0 swaps. The second time, with the second green arrow, we do 1 swap. Then the third element, we swap 8 2 times, right? 8 with 10, and then 8 with 9. 7 3 times, 5 4 times. So we have an orange arrow that gets always longer, okay? And if we add a longer array, 4, 3, etc., we would have always longer orange arrows. So what does this mean in terms of complexity? We can add up these numbers 0 plus 1 plus 2 plus 3 etc. plus n. Okay, we could rewrite this as the sum from 0 to n of e. Okay, we can use a mathematical formula called Gaussian sum that says that this sum here becomes n dot n plus 1 divided by 2. Okay, and in this in a case with 5 elements, for example, this means that 0 plus 1 plus 2, that is sum from 0 to 5 of e, 3, 4, 5 is equal to 5.6 divided by 2, that is 15. Okay, and this is real because 9, 12, 14, 15. So this is the Gaussian sum formula, and if we keep going, we do the multiplications, simplifications, etc. We have n squared plus n squared divided by 2 plus n divided by 2. And if you know theta complexity, we can ignore constants and smaller term coefficients and numbers, and we can concentrate only on the bigger term. In this case, bigger term is n squared. So we can say that insertion sort has a worst case complexity of theta of n squared.